All right, so now that we've seen kind of how we can get a matrix form of a transformation, we're going to talk about some special properties that these linear transformations have. So remember that when we started all of this, we were interested in linear transformations, which are just functions that have kind of two special properties, right? The idea is that if you transform one vector plus another vector, you get the same thing as if you transformed the vectors individually before adding them together. And it also has a property that if you multiplied the transformed version of a vector times a scalar, that's the same as multiplying that vector by the scalar first and then doing the transformation. So the idea is that we're going from some point x and using our transformation in this picture f to go to our codomain. Now, the range is what we're going to call the area of places we actually can get to with our transformation. We won't necessarily hit every possible value in the codomain. Sometimes we will, sometimes we won't. We'll talk about that. This is kind of our visualization of what's going on. We've got a set of values, and we send them to another set of values. And there may be a bigger set than the set we can actually reach talking about these things. So this is going to be lab 6. So kind of in the future, we're going to see several properties of linear transformations that are going to be useful for us to recognize. Back when we had our radiography lab, we talked about the idea that we would love to be able to take what we get from the machine and trace that back to figure out exactly what it is that we had object-wise kind of in the brain, in our scans that we have made. And so it's going to be kind of useful for us to understand a couple of these linear algebra properties so we can get there. So let's kind of jump down to a definition and get right into it. Let's say that we've got vector spaces V and W. V is our domain, W is our codomain. We say that a transformation going from V to W is injective if the following property is true. Whenever T of U equals T of V, it must be true that U equals V. So a transformation is said to be injective, is also said to be one-to-one or an injection. The idea is that any output corresponds to unique input. So maybe an example of this would be something along the lines, and this is not necessarily a linear transformation, but it's a function, f of x equals x squared. If we had this function, is f one-to-one? Well, if we look at f of 2, that's going to be 2 squared, which is 4, but f of negative 2 also equals 4. So here we can see that the answer is no. This is not a function that is one-to-one because there are two different inputs that give us the same output. So the idea is we want to be able to look at 4 and tell you for sure that I know what the input is. But if there's multiple ways to get to this output, multiple different inputs, then it's not one-to-one. And so this is the thing we'd like to see. We'd like to see injective transformations. It'll help us figure out whether or not we have something that we can kind of trace back to what we had before. So in order to show injectivity, we need to start with two arbitrary elements of the range of the transformation and suppose that they're equal. So suppose T of U equals T of V, and we want to work backwards to make sure that U and V have to be the same thing. If we can find two possible inputs to map to the same output, then it's not an injective transformation. So kind of a bit of a visualization here. Suppose this is our domain and this is our range. If we look at the range here, every single output that we manage to get to, there's only one input that goes there. If I have W1, I know it came from V3. If I have W2, it came from V1. W3 came from V5, and so on and so forth. W5 did not end up getting mapped to, but that's okay. We're only considering the outputs here that got mapped to. So the outputs, W5 doesn't happen to be considered an output, but all these other ones do. And when we have an output, we know exactly what input got us here. So this is one-to-one. This is another way of saying 1, 2, 1, just in case I end up accidentally using it later. By using this definition for the transformation, these are the outputs we get, right? So A, B, we know exactly what that does, and so we can use the C and the D to map out what the transformation is going to be here as well. And so here we get a number of different system or equations out here. A equals C, negative B equals negative D, B equals D, A plus B equals C plus D, 0 equals 0, and negative A equals negative C. The two that we need to focus on are the fact that A and C have to be the same and B and D have to be the same. So if this is the case, then A and C are equal, B and D are equal, so AB equals CD. So what we did is we assumed that the inputs were different, and what we found is that they had to be the same. And so by our definition, this makes that transformation one-to-one. We assume that we have the same output with different inputs, and then we have, if we can show those inputs actually have to be the same, then we get something that's one-to-one. All right, so let's look at a different transformation then. Suppose we wanted to look at a transformation defined going from P2 to R2, where we took an AX squared plus BX plus C, and we set it equal to A minus B and B plus C. This ends up being a linear transformation. You can kind of check the properties on your own in case you want a little extra practice. We want to know if T is an injection or is injective. This is kind of a way to show, if you want to show something's not injective, you just need to find two different inputs that give you the same output. So we can show that plus 4 when transformed here, that would be 1 for the B and 4 for the C, becomes negative 1, 5. And if we look at 5 minus x squared, that's negative 1 for the A, 5 is the C, B is 0, so we get negative 1, 5 again. And so different output, or same output, different inputs. So it's not going to be injective. But how could we have gotten there on our own? All right, so suppose for a second that we had started off the way we did the last page. So T of AX squared plus BX plus C equals T of EX squared plus FX plus G. This implies then using the transformation that A minus B, B plus C is equal to E minus F, F plus G. So matching up the entries, we get this as our augmented system. And so you could use sims to try to look at this once we put it into a matrix. So here we've got the A, B, and C. And we've got the E minus F and F plus G on the other side. And so if we row reduce this, what we're going to end up getting is a free variable, which means we'll have a little bit of room to play around with and see that we could change these inputs to get something that isn't a one-to-one transformation. And so we would want to go ahead and kind of pick some things to figure out for sure. So we could go ahead and pick an E, F, G and see if there was a way to get the same sort of E, F, and G, represent those with something else. So what we're going to do is if we let E be 1, F be 2, and G be 3, we'll get A minus B equals 1 minus 2, and B plus C equals 2 plus 3, so A minus B has to be negative 1, and B plus C has to equal 5. So then we'd get this system, in which when we solve for it, we'll get that A equals -1 plus B, but B is a free variable, and C equals 5 minus B. And so using this in conjunction with the stuff we have, we can pick a different value for B, and that will give us a different vector. And so here, if we pick B equals 1, then A is 0, C is 4, and that gives us x plus 4. And so we had -1 or -x squared plus 5, that would mean B is 0, which means A is -1 and C is 5. And so we have multiple different inputs to get us the particular output. So we have to kind of start off with the arbitrary matching of things and then try to move to a place where we can determine whether or not that every single part of the equation has to be equal, or if there's some things that maybe we don't know. So let's keep going. So that brings us then to our next definition, which is that of surjective. So again, we're going to let V and W be vector spaces. We say that the transformation from V to W is surjective if every element in W is mapped to. That is, if we have some element W in the codomain, then there is some V, so that T of V equals W. So a transformation that is surjective is also said to be onto or a surjection. So the idea is that we're going to do our best, or absolute worst, to present you with the most obscure element in the codomain. We want to make sure that we can map to, use this function to map to any particular thing, no matter what, whatever you have. So what we're gonna do is we're gonna pick an arbitrary codomain element and find some way to map to it. So consider that x squared we had talked about before. We talked about why it's not injective already. In fact, it's not even a linear transformation, but we can kind of use this to show that it's not onto either. So why is that? Well, if we're going from the real numbers to the real numbers, we need to make sure that every possible real number could be an output of this function, which is x squared. So notice, though, that x squared can never be negative. So it cannot be equal to -1. So in fact, there are no negative outputs. F of x is not onto. So we need to be able to get any possible output. So kind of use these ideas of injective and surjective to determine which of these following four figures that we're looking at, these four different pictures, are going to be injective and which are surjective. So here, domain to codomain, domain to codomain, domain to codomain, and domain to codomain. Just take a minute, try it for yourself, see what you get. Alright, so let's go ahead and take a look at these. We want to know if it's going to be one-to-one and if it's going to be onto. Well, to be one-to-one, or to be injective, 1, 2, 1, this is onto. In order to be one-to-one, we need to make sure every possible input or output has only one input. So this has only one, this is only one, this is only one. But no, when we get to W4, there are two different vectors from the domain that get there. So not one-to-one, C W4. W4 is our problem child. Now, in order for us to be onto, we need to make sure that every single element in this codomain is mapped to in some way, shape, or form. So W1, W2, W3, W4, and W5, they all have at least one vector going there. So, but it is onto. Okay, let's look at the next one. So here, looking at our outputs, if we want to show one-to-one, every single output has to have only one input going in. Again, W4 is the culprit, so this is not one-to-one. So again, we have to look at W4. But if we look, every single output, or every single possible thing in the codomain is mapped to. There's some arrow that points to it. So it is onto. Let's look at this one. If you look at all these different things that are mapped to, there's only one way to get to them. So is 1-to-1. But if we look at this codomain, W5 does not get mapped to. It's not onto. And then last but not least, we're going to check if this is 1-to-1 or onto. If we look at W4, there are two things going in, so it's not 1-to-1. See W4. And if we look at W6 and W7, they don't get mapped to at all. And so this is not onto either. W6 and W7. Okay, so this is just kind of a way for us to graphically look at and interpret these ideas of 1-to-1 and onto. Let's go ahead and try to find both of these things for one entire transformation. So let's let our transformation T go from R2 to M3/2 be defined as taking some A, B, and R2, transforming it into this transformation here. We want to go ahead and notice that we already showed this was a 1-to-1 transformation, and we want to know if it's onto. So the question is, if I compared this to something in M3/2, is there any possible thing in M3/2 that I can't get as an output to the function? If we look, we can't have anything where there's a non-zero in the bottom left-hand corner. So if we look at 1, 1, 1, 1, 1, 1, this is something that will never be an output of this transformation. So because of that, it's not going to be onto. So not onto. All right, let's look at something maybe that we can find both 1-to-1 and onto for. So suppose we've got a transformation going from R2 to P1 defined by taking and transforming an AB in R2 into a 2AX plus B. In order to show it's 1-to-1, we're going to assume for a second that we have two different inputs going to the same output. If we do, then this implies that 2AX plus B equals 2CX plus D. If we match up the like terms, we get that 2A equals 2C and B equals D. So comparing the thing that have the X's and the things that have just the constant parts. Here, we're able to see that A equals C and B equals D, which means that our inputs A, B, and C, D actually were the same thing all along. And so this is the definition of being 1-to-1. So we do get something that indeed ends up being 1-to-1. In order to show that T is also onto, we need to pick an arbitrary representative of the codomain. In this case, we'll just pick AX plus B. And we want to figure out if there's a vector that can map to get AX plus B as the output. So the idea is we're going to go ahead and take some CD as our input, and if we transform CD using our function, we get 2CX plus D, and we want to know if there's an arbitrary AX plus B that we can get. So I don't know what A and B are, but I want to make sure, since it's some random thing in P1, that I can get it. So again, we'll create a system of equations. We'll compare our coefficients for the X portion. We'll compare our constant portions. And what we get is a system of equations that says that 2C equals A and D equals B. And we can see from this that C equals A over 2 and D equals B. So the question really is if we could find some way of getting AX plus B no matter what it was using our function. So because there is at least one way to get to any element of the codomain T is onto. And so since we're able to go ahead and create a map that'll get us there, we're able to say that this is an onto transformation. All right, so in the next video, we'll be talking a little bit more, another ICE 5 numbering system messed up. So this will be ICE 5 kind of part 2. And what we'll do is we'll try to see if we can create some transformations that have these different properties.